So last night I posted a video about the history of crystallography leading up to modern crystallography. So it kind of covers the key components from about the 17th century up into the early 20th century. And that's there for you to review in addition to the lecture notes. Today we're going to start talking about crystals. And crystals can be divided into two different areas of information. One is what's called the lattice and motif. Lattice is how it repeats, and motif is what is repeating. Is it a molecule? Is it a region of space? Is it a couple of atoms? The lattice is how it repeats. So when we look at examples of lattice, you can have one-dimensional lattices, two-dimensional, and of course three-dimensional lattices, which are where we get unit cells from. And then later on next week, we'll be talking about crystals in reference to space groups and the asymmetric unit. Space groups are groups that contain certain types of symmetry elements in them. So we're going to be talking about symmetry elements next week. And space groups are contained in different crystal systems. And we can have, within these crystal systems, we can have different types of centering that we talk about in addition to the symmetry elements. To give you kind of a layman's term about crystal system and space groups, if you think about meat, we have different types of meat. We have beef, chicken, pork, and lamb, for example. So those are kind of like the crystal systems. So in crystallography, we have, as we'll see later on, we have 7 types of crystal systems, just like we have in this example 4 types of meat. Now within the crystal system, we have space groups. And so you can think of space groups as the type of cut of meat you want. So for example, for beef, you could have a T-bone, ground beef, ribeye. For chicken, you could have quarters, chicken breasts, legs, etc. And that's kind of like how crystal systems and space groups work. So crystal system is a broad category, like what type of meat it is. Space group is more specific. So for example, the type of cut of meat. And we'll be talking about that next week when we introduce symmetry in crystal systems. And so a crystal, as I've said in the history, it has to be a solid. So we're only talking about crystalline solids, and it has to have an order array that gets repeated periodically in 3 dimensions. So if it doesn't have this long range ordering, it cannot be a crystal. And an example of something that doesn't have long range ordering is an amorphous solid, such as a glass. Doesn't have long range ordering. And so when you put a glass fiber in an X-ray beam, you don't get any diffraction because there's no periodicity in the solid. And so this order array we refer to as a lattice. It's a regular repeat pattern in the crystal. And for a crystalline lattice, it must fill 3-dimensional space. And so we have different types of lattices. We have a one-dimensional lattice, which is a row lattice. So here the individual A is what gets repeated in 1 dimension. So the A gets repeated to infinity in a one-dimensional row lattice. In a 2-dimensional lattice, the repeat unit, in this case, the repeat unit is a B. It gets repeated in 2 dimensions. And it's referred to as a net lattice. Now, what we're mainly interested in is a 3-dimensional lattice, which is called a space lattice. So here, the C, which is the repeat unit, or which is the item that gets repeated in 3 dimensions. So you go X, Y, and Z, you see that the C gets repeated in the 3-dimensional space. And so C is the repeat unit that is repeated. And so this is what we mean by a lattice. It has to have something that gets repeated periodically, depending on whether it's first, second, or third dimensional lattice type. So here's just showing you some examples. It doesn't have to be the exact thing. You just have to include something that gets repeated in 3 dimensions. So for the first example, the repeat unit is this up arrow, and it gets repeated in 1 dimension, the same thing repeated over and over. But it can contain more than just one thing. So here we have an up and down arrow. Again, it gets repeated across the row. So the same repeat unit in 1 dimension. So the key thing is to find what gets repeated in the lattice. And then the last one, we have up arrow, down arrow, and a dot, and that's the repeat unit for this lattice here. Now, for example, if I just said in the last example, if I just said that the repeat unit was just the up arrow, well, this would not be a lattice point because it's not getting repeated periodically, because after the up arrow is a down arrow. So just saying that the up arrow is the lattice point would be incorrect. The lattice, what gets repeated is the up arrow, down arrow, and the dot. So that's what gets repeated along the 1-dimensional row. So you have to include everything that gets repeated. You can't just include the up arrow because it doesn't get repeated periodically. It's the up arrow, then the down arrow, then the dot. So all of these 3 items get repeated in the 1 dimension. So there are some rules for lattice points. The first one is it has to translate infinitely and be repeated. So translates means the only difference between one lattice point and another is that it's been moved 1 unit either in the X, Y, or Z position. And it has to have something that is repeated throughout the crystal. And then, as we'll see in a second, each lattice point must have the same spatial relationship with all the other surrounding lattice points. And we'll look at some examples of what that means in just a second. The third bullet is very important. A lattice point doesn't have to necessarily be an atom. So when we think of unit cells, we think of sodium chloride, where the lattice point is an ion of chloride. But in some cases, it may not even be an atom or a molecule. It could be a region of space that meets the first 2 criteria. So just to let you know, lattice point doesn't have to be an atom or molecule. It can be a region of space. The lattice points have to meet these criteria in order to be a valid lattice point. So here we're looking at a couple of lattice points, and so I've circled the point with the red X next to the flower, and you see that this point is related to the next point along the A or X axis by translation. And the way we know this is translation because the only difference between this point and this point is we added 1 to the X value. So these are lattice points of each other. And notice that its spatial distance from the flower is the same in each lattice point. So it's the same distance from the flower. And then if we were to look at the next one, so this lattice point, this would be 2 plus the original X, Y. So again, all we're doing is we're translating along the A-axis, which in crystallography refers to the X-axis. So since we're only translating, these are lattice points, because the only difference between these 3 points is translation along the X-axis. So we're just moving 1 unit to the right for each one of these lattice points. And then if we went to the 4th point, it would be 3 plus X, comma Y. Now, if we were to drop down, so So say instead of going to the right, we took this point here and we moved down 1 unit. So you see the B axis is coming down. B refers to the Y axis in crystallography. So if we move down 1 unit, what is the relation to this lattice point from this one? And so if we were to show the relationship, it would be 1 plus X, 1 plus Y. Because it's moved 1 from the original X and it's moved 1 down from the original Y. So it would be 1 plus X, 1 plus Y lattice. And then if we continue down to the next one, this would be 1 plus X and 2 plus Y, because we've moved 2 units down the B axis, or referred to as the Y axis. And so now what we can do is, once we've determined all the lattice points, we can find or define a regular repeat unit that gets repeated in the 1, 2, or 3 dimensions. So what we're seeing here is we've taken these 4 lattice points, this one, and this one, and we've made what's called a unit cell. So if we connect these 4 lattice points, this is what gets repeated in 2 dimensions. And so now if we move to the left, you see we have the exact same thing that gets repeated. It looks exactly the same. The only difference is from the green square to the red square, we've just translated the lattice points. Or if we go to the right, we connect these 4 lattice points. Again, it's the same as the green one, except we've just translated it across, in this case, the X axis. So the blue, green, and red are the same repeat unit, and so these squares are referred to as the unit cell. So in this unit cell, you have a flower with all this open space in it. And so this is what gets repeated in 2 dimensions. It's the same exact box with the same exact items inside the box. Now, for example, let me clear these out. For example, let's say we decided to call this a unit cell. So we looked at this lattice point, we connected it, and we formed a new unit cell, and we say, okay, we're going to define this as the unit cell for this 2-dimensional lattice. But what you'll notice is when you look at let's say we go down and we connect. So the new unit cell doesn't have the exact same components as the original unit cell. So that means that this unit cell cannot be a unit cell because it's not exactly repeated in 2 dimensions. So whatever you define as your unit cell has to be exactly the same thing that gets repeated in 2 dimensions. So if we define this blue square as the unit cell, this is not a valid unit cell, because when we shift it down, you see we don't get the same thing as what's in the blue square. And since it's not the same thing, it doesn't classify itself as a unit cell. So we didn't, in that case, those lattice points did not make a unit cell, or they're not valid lattice points, is what I should say. So here if we look at sodium chloride, so these are what crystals of sodium chloride look like. This is what the molecular view of sodium chloride crystal looks like. So you can see we have chloride and sodium ions that pack in a way that forms a crystal. And so if we were to slice this crystal, this is what we would see in the crystal. So this is what gets repeated in 3 dimensions with a sodium chloride crystal. Now, if we were to take that crystal and define some lattice points, so let's say, for example, we wanted to define a lattice point as one right here, here, and here. So these 4 points define the lattice point, or lattice points. If we were to connect them, we would get a unit cell. And you'll notice that this unit cell gets repeated in 3 dimensions. So if we go up, it's the exact same thing that keeps on being repeated over and over. And so since it gets being repeated over and over, this could be a valid unit cell for this. Of course, this is only a 2-dimensional net lattice, not a 3-dimensional space lattice for sodium chloride. So now if we were to take this 2-dimensional view and transfer it to a 3-dimensional view, this is what the space lattice of sodium chloride looks like. I think it's sodium chloride. No, it's not sodium chloride. It's just an example of a space lattice. So each one of these are lattice points that get repeated. And when we connect a certain number of lattice points, it becomes a unit cell. So in this example, we connect the green and blue dots. Oh, this is sodium chloride, my bad. You see, we get a basic repeat unit in this space lattice. So all of these get repeated in 3 dimensions. So if we shift to a new set of lattice points and connect them, we get the exact same thing here. So we connect these green ones. Again, we get the same set of lattice points as in the first unit cell. And so for a crystal of sodium chloride, if this was the unit cell, if you look here, we have, let's see, the blue spheres represent chloride, the green spheres represent sodium. And so we have 4 blue spheres, which is chloride, and 4 green spheres, which is sodium ions. The reason I'm showing you this is because from the unit cell, you can actually deduce the formula of your compound. Now, this may be a little bit out of the blue, but if you can remember from Gen Chem 2, when you talked about solids, when you have a atom or ion on a corner of a unit cell, it's actually 1/8 of an atom. And so since all the blue spheres are on corners, so if we take 4 times 1/8, this is 1/2 a chloride ion. And then we do the same thing with sodium's ions. Since each one is on a corner, we have 4 times 1/8 equals 1/2 sodium ion. Now the number of ions is not very important, but what you should see is that it has the same number. So there's 1/2 chloride and 1/2 sodium. So this is a 1-to-1 ratio, and that's correct because sodium chloride is 1-to-1. For every 1 chloride, there's 1 sodium. So in this unit cell, for every 1/2 sodium, we have 1/2 chloride, which is correct because it's a 1-to-1 ratio. So by knowing the components of the unit cell, you can, in some cases, easily determine the formula of the compound in that unit cell. In sodium chloride is a very simple structure to look at. If it was something more complex like organic compounds, it's not as easily visualized as it is for sodium chloride. So here talking about unit cells because it's the most important component here in a crystal, because once you know what's in the unit cell, you can generate the entire crystal. And so as we said earlier, a unit cell is the basic repeat unit of a crystal. And the repeat unit means it contains all the symmetry of that crystal in the box in that unit cell. So when you have a unit cell, everything that's in the unit cell has been generated through symmetry. The only difference is now when we add these unit cells together, we're just translating. We're not doing any more symmetry. So symmetry is used to build what's inside the unit cell. And we'll talk about symmetry next week. So in order to understand what's inside the unit cell, we have to use symmetry to generate everything inside of the unit cell. Now, once we have the unit cell, the crystal is just made up of repeating the same unit cell over and over. So it's as we call a blueprint or template for the whole crystal. Now, these unit cells, they retain all the properties of the crystal. So if you calculate the density of one unit cell in the crystal, it's going to be the same as the density of another unit cell in the crystal. There's no change in its properties of that crystal when you go to a different unit cell in the crystal. They're exactly the same copy of that box. So it just gets repeated in 3 dimensions. And so unit cells come in all different shapes and sizes. There are actually 7 different types of unit cells depending on the crystal system. And we'll talk more about those types later on next week. But again, there are 6 parameters that make up a unit cell, which are called lattice parameters. And as you see here, these are the lengths A, B, and C, which correlate to the X, Y, and Z axes, and then the angles between the different axes, which are alpha, beta, gamma. Now, an easy way to remember what axes make up the alpha angle, beta angle, and gamma angle is to think of alpha as A, and so alpha is the angle between B and C. So if you think of alpha as A, you disregard the A, and what's left are the axes that make up the alpha angle. Next we have beta. Think of beta as B, and that tells you that the axes that make up beta are A and C. And then lastly we have gamma. Gamma we can think of as C, and so gamma is the angle between A and B. So that's an easy way to remember the different angles. Now, crystal systems are based on restrictions in lattice parameters. So based on these restrictions, we get 7 different types of crystal systems. And within those systems, we have certain groups of symmetry elements. To give you one example, cubic is a crystal system. And it has the following constraints. So A has to equal B equals C, and alpha equals beta equals gamma, which equals 90. So if your unit cell fits these restrictions, it's going to be a cubic unit cell. Now this is just one of 7. We'll talk more about the others later on, but this is just kind of give you an example of what we mean by restrictions to the unit cells. So we have restrictions on the lengths and restrictions on the angles. And cubic is probably the most restricted crystal system that we have out of the 7. Now later on, I would recommend that you click it on this link here, and it'll direct you to a little short video giving you a visual representation of crystal lattices and unit cells. So now we're just going to look at identifying types of different unit cells you can have based on the lattice points. So here we have this hippo drawing, and we've identified some lattice points on it. So the left eye of the hippo are the 4 lattice points that we've connected in this fashion. And so if we connect them like this could be a unit cell, because if we go to the left and do the same thing, we get the exact same thing as we did with the green box. So that is a valid set of lattice points that make up the unit cell. And it's the exact same thing. So if we drop down, again, we get the exact same information in the unit cell. So that's one way we can connect these 4 lattice points. Another way we can connect them is not as a square, but as a parallelogram. So here we're connecting the 4 lattice points in a little different fashion. And now if we were to connect it, go up and connect, we can't just go up, let's go to the side. So we would go to the side and connect. You see we get the exact same thing inside the unit cell. So that you can connect the 4 lattice points this way as well and get the same copy each time you translate those lattice points. And then lastly, we can connect them in this fashion shown here. Now if we were to shift this up 1 unit, change color. We get the exact same thing. So there could be many different ways you can connect a series of lattice points so that you get the exact identical information when you connect them into a unit cell. So there were 3 different ways we could connect these lattice points. So again, the lattice points we defined as the left eye in the hippo. So sometimes lattice points could be on the corners of a unit cell, or you can have, you know, lattice points that may not necessarily be in the unit cell, but this, like for example here, the whole hippo is inside this box. The main thing is that the exact same copy is found as you translate along the different axes. So if you look at one box compared to another box, you get the exact same thing. So here I want you to take a few minutes, and I'll give you a few minutes to work on this, but I want you to look at each one of these unit cells that have been connected by a series of lattice points and determine which ones are unit cells and which ones cannot be unit cells. So take a few minutes, kind of look this over, and see if you can identify which ones are and are not. Give you about another minute or so. Okay, let's take a look at these. So let's see which one of these could be unit cells. So for example, if we take the top square here, so this one here, and we translate it, let's say we're going to move it, shift it down. What you notice here is that the new unit cells information is not the same as the original. So this one would not be a unit cell because you don't get the same repeat unit when you connect those four lattice points. So that can't be a unit cell. Now if we look at the next one, we have this parallelogram connecting these four lattice points. If we shift, let's say we shift down, and connect those another set of those four lattice points, you see that the information in the new unit cell is similar, is the exact identical copy of what was in the original unit cell. And likewise, if we scroll up, not scroll up, but if we go up like that and come down, we would again have the exact same copy. So this one is a valid unit cell. because when we translate that unit cell to a new set of translated lattice points, we get the exact same copy of information. If you're not convinced, we can go this way. So if we come this way, and connect the lattice points, we get the exact same thing. So this one is a valid two-dimensional unit cell. Now if we take a look at the middle one here, and if we were to translate this so we translate it along this direction, and if we go back as well, here is not, we're not getting the same repeat unit. So this should be chocolate, white, but then we have white, chocolate. So this wouldn't be a correct unit cell because the exact same thing is not getting repeated. It should be chocolate and then vanilla, but then we have vanilla and chocolate. So this one would not be a valid unit cell. Because again, you don't have the exact same repeat unit that gets repeated. Now if we look at the next square, so here we have this as our original set of 4 lattice points. If we scroll up, not scroll up, but go up and connect the same lattice points that have been translated, oh, I didn't do that right. Oh. You see that we get the exact same information in the new unit cell. And if we go down, again, we get the exact same copy. So this set of 4 lattice points would make up a unit cell because it's the exact same thing that gets copied in the 2 dimensions. So we went this way. Again, we get the same replica. So that is a unit cell. We look at the last one down here. See if I can copy this. Let's white. So we just translate it. We connect the new set of lattice points. You see we get the exact same copy as what we originally had. Now if we move up, I'm sorry I can't draw a straight line that well, and come down, again we get the same set, the same information in the translated unit cell. So these 4 lattice points that are connected here can form a valid unit cell. So again, when you're connecting lattice points to make a unit cell, what you're looking for is the same thing is getting repeated every time you draw a new unit cell. You've just translated it along the X, Y, or Z axis. So here was just kind of zoom in on that one that was slanted and explain why it wasn't a valid unit cell, because if we repeat that same set of information, you see we don't get the same repeat pattern as what's shown on the left. So this is the crystal shown here of these bugs. And if we're going to cut out this as the unit cell that's going to get repeated in 3 dimensions, when we or 2 dimensions, when we start repeating it, we notice that what we're getting is not what the crystal looks like. So we're getting, half chocolate, half vanilla bugs, when we should get, a bug that's totally vanilla or totally chocolate. We can't get, a bug that's 2 different colors. That's not what the crystal represents. And that's why this one is not a valid unit cell. So if we're looking at these examples, so out of these 4 examples, I would like for you to take a few minutes and see if you can identify which one or ones of these proposed unit cells is not a valid unit cell. And I'll give you, 2 or 3 minutes to take a look at it, and then we'll go over it. About another minute. Okay, so if we take a look at these, we'll look at A. We'll start with A. So A says the unit cell is these 4 lattice points. So as we repeat these set of points in 2 dimensions, you see we get the exact same thing, and it accounts for the entire space in the crystal. Now for B, what we've done is we've assigned lattice points for the empty or unshaded dots. So in A, what we did is we defined these shaded dots as the lattice points. And each unit cell in A contains, in the center of it, one unshaded circle. Now in B, we've defined the unshaded circles as lattice points, and inside each one of those, we get a solid circle in it. So again, B is also a valid set of lattice points because, again, the same thing gets repeated in 2 dimensions, and we let's see which word I'm looking for. And all of the crystal is accounted for. Now if we come to C, we've increased the size of our unit cells. So you can notice in A and B, we have small unit cells, but in C, we decide that we're going to include two unshaded and one shaded lattice point along one direction, and then two unshaded, and then a shaded one as well. So we've increased the size of our unit cell, but this is okay as well because it includes all of the crystal, and the exact same thing gets repeated in 2 dimensions. So A, B, and C are valid unit cells. What you're seeing the difference in A and B is what lattice points are we connecting to make the unit cell. And then C, we're creating a larger unit cell than what's found in A and B. Now when we get to D, we define these 3 lattice points as a unit cell. And as we repeat this unit cell in 2 dimensions, you see we get the exact same thing as what we started with. However, the one thing that's important here to note is that we don't account for all of the space in the crystal. So our unit cell is missing this information here. So our unit cell doesn't account for everything in the crystal because it's missing this blue region right here. So this one would not be a valid unit cell because it doesn't include all the unique component of the crystal. So it's missing the other half of that unique component of the crystal. And so D is the one that is not a unit cell. So here we're just going to have some fun and draw some lattice points, connect some lattice points that could represent a unit cell. So let's see what we have here. So one thing we could do is we could connect, let's see, we'll start with something small. So obviously we couldn't just connect these 2 red and gray dots, because if we were to translate this, we notice that we don't include everything in the unit cell. So not all of the unique components of the crystal are found in this proposed unit cell here. So this one, obviously, we cannot make a valid unit cell. But what we can do now, if we did this, so let's say we connected these 2 gray dots, and we connected it like this. So now if we were to translate this, let me switch the color. You see that we account for all the unique component of the crystal, and we get the exact same repeat unit. Let's see, is that correct? No. Well, I stand corrected. No, because if we do it this one, you notice we don't get the same repeat unit. So actually, this is not a valid unit cell. So let's correct this. So what about if we do we define the unit cell like this? So we made it bigger to include all the unique components of the unit cell. So now if we go up, I can't really draw a straight line. I apologize for that. So in that direction, we get the exact same thing. Now if we go to this direction, again, we get the exact same copy. And if we go to that one, we ran out of space because we don't have a big enough template. Yeah. And so this is a valid unit cell. So if we connect these lattice points into a unit cell, the same thing gets replicated in 2 dimensions. Now we could only stop here because if we make any more unit cells, we would run out of space in the diagram shown here. So that's one possible unit cell. Let's see if we can do one more and then we'll move on. Let's try to do a smaller one. So let's say we connect these 4 blue dots. Can we replicate what we find? And so if we go to the next one, you notice what's in the first unit cell is not the same as what's in the second unit cell. So this one would not be a valid unit cell. What about if we include a series of 3 blue dots? So now if we translate, so that one is identical, so that's good. And if we shift down, but you notice that when we shift down though, we don't get the same repeat unit. So this is not a valid unit cell. What about if we do this? We make this the unit cell. Now if we go to the right, we get the same repeat unit. And if we were to see if I got any, well, we ran out of space. But I believe this would be a unit cell as well. Yep. So sometimes you have to increase the size of the unit cell to make sure you fit all the unique information about the crystal inside the unit cell box. So now we're just going to look at a few quantitative calculations involving unit cells. I'm going to stick with the very simplistic ones, and that's the cubic unit cells. Cubic unit cells. And as I said, the constraints for lattice parameters on cubic unit cells is A equals B equals C, and alpha equals beta equals gamma equals 90. So the only unique aspect of a lattice parameter on the cubic unit cell is the length of the cell axis. And there are 3 types of cubic unit cells. One second. These are simple cubic, body centered cubic, and face centered cubic. So simple cubic, there is an atom or ion located, there is an atom located on every corner. So for a simple cubic unit cell, you can only have 1 atom in it. So you would not see a simple cubic unit cell for an ionic compound because the minimum number of ions you need for an ionic compound is 2. So simple cubic could be observed for elements, because elements, only need to contain one atom. But ionic compounds will never be simple cubic. Next, we go to body-centered cubic. So we have, again, the atoms on the corners, and we also have an atom in the center, atom or ion, in the center of the unit cell. And so for body-centered cubic, you can have a maximum of 2 atoms. So one atom comes from having an atom on each corner, because remember, a corner is an 8th occupied. So 8 atoms times 1/8 gives us 1. And the atom in the center is a whole atom, so that's a total of 2 atoms. So ionic compounds could be body-centered cubic. Now with face-centered cubic, we have an atom on each corner and an atom on each face. So again, from the corners, that represents 1 atom, because again, each corner touches 7 other corners, so an atom on the corner is 1/8 of an atom. And then on the faces, each face touches another face, so an atom on the face is 1/2 an atom. So for face-centered cubic, you can have a total of 4 atoms or ions. So so face-centered cubic could crystallize for a ionic compound. Now we're just going to look at some calculations involving cubic unit cells, and these are also the calculations are similar to other types of crystal systems. It's just the equations are a little bit more complicated than they are for cubic. So things we're going to calculate are the density and the radii of atoms or ions. So we can get those 2 pieces of information by knowing the unit cell. So here we have polonium, and polonium is one of the few elements that crystallizes. That should be simple cubic, not face-centered cubic. So simple cubic unit cell. So polonium is one of the few elements that can crystallize in a simple cubic unit cell, and I've got a little diagram of what a simple cubic unit cell looks like. And we want to calculate the density of polonium in grams per centimeter cubed. And so what we're given is the length of the axis A. Now remember, for a cube, A is the same whether it's length, width, or height, because A is the same for B and C. And so we want to calculate the density of polonium. Density is mass over volume. So what we need to look up is, first we need to calculate the mass of polonium, and then we need to calculate the volume of polonium. Now to calculate the mass, we have to remember that in a unit cell, how many atoms of polonium are there? And that is 1 atom. So each unit cell of polonium has 1 atom. And if we need to find mass and we have atoms, you have to think back to Gen Chem 1. And if we had entities, how do we find mass? And the answer is, we have to first convert to moles and then to mass. So when you know the number of atoms in the unit cell, you're going to you're going to divide by Avogadro's number, because 1 mole is 6.022 e to the 23rd atoms. So this will give us moles, and then we can multiply by the molar mass to give us the mass of 1 atom of polonium. So let me look up polonium. I don't have a periodic table. So it's 209 grams per mole. So we're doing all of this to determine what's the mass of polonium when we have a unit cell, a simple cubic unit cell. And it's going to be really small. So we get 3.471 e to the negative 22 grams. And so that's how you find the mass of polonium in a simple cubic unit cell. So you have to remember that simple cubic means it's only going to have one atom. We convert that to moles. Then we use molar mass to convert it to mass. Now we need to calculate the volume. Move that up. So remember, the volume of a cube equals the side, which is A, cubed. So if we know the side of the cube, I know there's a lot of cubes here, but if we know the side of the cube, we can cube that value to find the volume of a simple cubic unit cell of polonium. Excuse me. What we have to remember that is A is in picometers, but we want density in grams per centimeter cubed. So we need to convert this A into centimeters. So if we want to convert it to centimeters, we have 3.34 e to the second picometers. One meter is 10 to the 12 picometers, and then 100 centimeters in 1 meter. This is how you convert between picometers and centimeters. So we convert first to meters and then to centimeters. So this becomes 10 to the fourth, I believe it's 3.34 e to negative 8 centimeters. Let me double check. Yeah. And so that's the length of the a-axis in centimeters. Now we can plug it into the volume to find the volume, or the volume equation to find the volume of this unit cell. And this would be in centimeters cubed. So now we have the mass, we have the volume, we can calculate the density. And we get the density to be 9.32 grams per centimeter cubed. And this is how they use crystallography to determine the densities of solids. So if you know the unit cell parameters, you know how many atoms are in the unit cell, you can determine the density of that substance. Now, this is easy for cubic unit cells, but the other types of unit cells, it can be a little bit more involved, meaning the process is the same. The only difference is the volume equation is a little bit different for the different types of crystal systems. So this is how you calculate density when given the length of the a-axis for a simple cubic unit cell. Let me see for the next question. All right, let me go back. So now we're going to look at how do we calculate the radius of the polonium atom. Let me clear all drawings. So again, we're dealing with polonium. We know that it crystallizes in a simple cubic unit cell. The length of the A-axis is 334 picometers. What's the atomic radius of polonium? And to answer this question, you have to look at the diagram at the right, and you see that A is equal to 2 times the radius of polonium. Because if you look here, when A, which is this length here, it includes 2 halves of an atom. So this is R, and this is R. So if you wanted to find out what the radius is, the A-axis for a simple cubic unit cell makes up 2R. And that's where the 2R comes from when we set A equal to that, because there are 2 R's along the A-axis. So now what we can do is, if we know what A is 334 picometers, is equal to 2R. R is just simply dividing 334 by 2. 167 picometers. So that's the radius of a polonium atom. Likewise, if you knew that polonium crystallized in a simple cubic unit cell, and you knew the radius of polonium, you could calculate the length of the A-axis just by doing the opposite of what we just did. So again, simple cubic unit cell, very straightforward in regards to the calculations. Now we're going to go to a little bit more complex unit cell, which is a face-centered cubic unit cell. And calcium crystallizes in a face-centered cubic unit cell. And it tells us that the length of the A-axis is 558 picometers. Calculate the density of calcium. So in order to calculate the density, we need to know the mass of calcium in this unit cell and the volume of calcium. And so here with face-centered cubic unit cell, you have to remember, okay, what's the total number of atoms in a face-centered cubic unit cell? And the answer is 4. There are 4 atoms in a face-centered cubic unit cell. So with knowing that, we can calculate the mass of calcium in the unit cell, and knowing the A-axis, we can calculate the volume of the unit cell. So the volume is just A cubed, because again, it's a cube. We convert the A-axis from picometers to centimeters. Just double check that. And that's actually not the right value. It should be to the -8. So let me make that correction. So that should be to the -8. Now that we know this A, we can calculate the volume. So let me make sure that's correct. Yeah, that is correct. So that is centimeters cubed. So now we know the volume of our unit cell. We need to calculate the mass of calcium. So again, the total number of atoms in that face-centered cubic unit cell is 4. So now we can determine the mass of calcium. So again, 1 unit cell, there's 4 calcium atoms. We convert that to moles, multiplied by the molar mass. We get the mass of calcium in this unit cell. Now that we know the mass of calcium and the volume of calcium, we can calculate the density. And the density here is 1.53 grams per centimeter cubed. We just have one more example, and then that'll finish up today's lecture. And this involves nickel, and nickel is a face-centered cubic structure. And it says the density of nickel is 8.908 grams per centimeter cubed. What is the length in picometers of an edge of the unit cell and the radius of nickel? So here we're given the density and asked to determine the length of the A-axis and the radius of nickel. So first we need to determine the number of nickel atoms in the unit cell. This should be nickel, not calcium. And since it's face-centered cubic, it's going to be a total of 4 atoms in the unit cell. Now that we know the number of atoms, we can calculate the mass of nickel in this unit cell. So now that we know the mass and we know the density, we can calculate the volume. So volume is just mass divided by density. We get the volume of this unit cell. And since this is a cube, volume is equal to A raised to the 3rd power. And so we can solve for A. So we get that the length of the A-axis is 364 picometers. Now we need to determine the radius, and we have to refer to this picture right here. And this picture tells us that A squared plus A squared equals D squared, and this is Pythagorean theorem, and so D squared is actually 4R squared. So if we know what A is, we can determine the radius of nickel. So we square the A. We set it equal to 4R squared. We determined that the radius of nickel is 129 picometers. Now this A squared plus A squared equals 4R squared is the same for any face-centered cubic unit cell. These are just some of the calculations you can do with unit cells. You can calculate the volume, you can calculate the mass, you can calculate the radius of an atom if it's a cubic unit cell. So that concludes today's lecture. I'll stop the sharing, and if you have any questions, you're welcome to ask.